So one thing that you probably noticed by now is that when we're talking about something that pulls down to ground, we're only using the NMOS devices to pull to ground, and we're only using the PMOS devices as a network to pull up to VCC. And the reason for this is what we call the signal strength that can go through the transistors. So when you talk about the signal strength, the strength of your signal is how well does it and how close does it approximate the value of the ideal voltage source. So in this case, we're talking about two voltage sources. We either have VDD, or our high voltage, or ground, which is our low voltage. So obviously VDD and ground are the strongest one for VDD, and the ground is the strongest zero that we can possibly have. Now when we look at the transistors themselves, an NMOS device can pass a strong zero. In other words, the NMOS can basically pull your output all the way down to zero if you give it enough time. Obviously you have delay in actually pulling charge off of some capacitor, but an NMOS can pull your output all the way to zero as long as nothing is fighting it. But if you connect an NMOS up to VDD, it can't actually pull your value all the way up to the 1, all the way up to VDD. And that's because the NMOS, if you have your NMOS gate at VDD, it can only pull the output up to the VDD, the gate voltage, minus VT, which is your threshold voltage of your NMOS. And so you don't quite get all the way up to VDD. And so it basically creates what we call a degraded or a weak one. It's trying to pull up to VDD, can't get all the way there. Similarly, your PMOS device can pass a strong one. If you connect your PMOS gate to ground, it can pull the output all the way up to VDD eventually. Again, it takes some time, but as long as you don't have anything fighting it, PMOS can pull the output all the way up to 1. So it passes what we call a strong one, not quite as strong as actual VDD rail, but a pretty strong one. But again, similar to the NMOS, but flipped, complementary to it, it can't pass a full ground value through it. So if you connect the PMOS gate up to ground and you try to use the drain of the PMOS also connected to ground and tried to pull your output based on the PMOS, it can't pull all the way down to ground. It can pull down to ground plus your threshold voltage. And that's all the farther that it can get before it turns off. So NMOS are best for your pull down network to pull down to ground, and PMOS are best for your pull up network to pull to VDD. So we've said several times in the past that transistors can basically be thought of as switches. So we can use our NMOS and PMOS transistors as if they were switches. And up until now, we've been looking at them in terms of pulling to ground or pulling to VDD as an NMOS network or a PMOS network. But what if we think about them in terms of if we had an output of a gate and we just wanted to use the transistor as a switch to connect it to something else? So you can, let's look at the NMOS transistor at the top row here. If we have the gate of an NMOS transistor connected to 0, it doesn't allow the signal to go through. So it's an open switch. And we get nothing at the output from the source to the drain. If the gate is connected to 1, though, we do have a connection from source to drain, and it's a switch that's closed. However, if we just have a single NMOS connected from the output of some logic gate and going someplace else, if the gate is 1 and the switch is actually closed, if that input gate, or if that gate that's driving this transistor switch of an NMOS is driving a 0, you can see, based on what we said in the previous slide, that it will pass the 0 pretty well. It can pass a 0, a strong 0. But if that previous gate is trying to drive a 1, you can see that an NMOS transistor doesn't drive a 1 very well. It drives a degraded 1. And so it doesn't do a very good job if we just wanted to use a single NMOS transistor as a generic switch for both types of logic values, 0 and 1. It does a good job at 0, not a good job at 1. Similarly, or complementary to that, the PMOS transistor on the bottom, if the gate of a PMOS transistor is 0, it will be a switch that's closed and has a connection. If the gate value of the PMOS is 1, it will be an open circuit and it won't allow anything through. So let's look at what happens if we actually have the gate connected to 0. The switch is closed, but in this case, if we're trying to drive a 0 through the PMOS transistor, it does try to drive it, but it doesn't drive a good 0. It drives a degraded 0. And if it's trying to drive a 1, it does a good job, and it can drive a strong 1 through. So you can see each of the two transistors, if we try to use it as a switch, work well for one set of logic, but not well for a different set of logic. So what do we do with that? So if we want to create a logic gate that can pass both a 0 and a 1 well, we can't just use a P or an N device singly by itself, because the pass transistors, both PMOS and NMOS, for one of the logic types will produce a degraded output. So what we wind up using is what we call a transmission gate that can pass both a 0 and a 1 well, and this is the circuit structure for it. It is shown below here now. And this is, we use both the N and the PMOS, and we've taken N and PMOS transistor and put both of them in parallel with each other. So we take the source of each, the N and PMOS transistor, and connect them together for the input, and the drain of both the N and PMOS and connect them together for the output. You can see in this case, the gates are not connected to the same value. The NMOS gate is connected to gate value G, and the PMOS will be connected to GB. This is a notation formality that it's used quite often. It means G bar, or inverse of the value of G. So often you will see some net name or pin name that when they put a B at the end, typically they mean it's the bar or inverse version of the signal without the B at the end. So when we do this, you can see if G is 0, that means GB is 1. Both the NMOS and PMOS are turned off. They're switches that are open, and we have no connection from A to B. And so we have no drive from this particular gate on the net B. If G is 1, GB is 0, that means both the NMOS and PMOS device are turned on, the switch is closed, and we have a strong connection between A and B. In this particular case, the NMOS device will actually connect from A to B and drive a strong 0. The PMOS device will drive a weak 0, but it doesn't matter, it will be kind of overridden by the NMOS device being able to drive the strong 0. If, however, there's a 1 coming from A, the PMOS device will be able to drive a strong 1 output, and so even though the NMOS device is driving a weak 1, it'll help out a little bit, but the PMOS device will do, most of the work to get up to the value of 1. So this type of gate can be used as, in effect, a switch. The combination of the NMOS and PMOS are used together as a switch that can drive both a strong 0 and a strong 1. We just need a G and a G bar, so we need a complementary value going to the two different gates. On the bottom row, you can see these are three different symbols that are used to denote what the transmission gate structure is. And I've seen all three of them used in different places. They can be used interchangeably. I tend to use the one that's on the lower left most often personally, but I've seen all three used in different situations. So up until now, we've pretty much always been talking about complementary logic, where any type of logic gate that you design, you want to make sure it has either an N stack that is driving a 0 out or a P stack that's driving a 1 out, and you don't have any unknown values coming out of your logic gate. Now I'm going to talk about a tri-state buffer. Tri-state buffer is called tri-state because it can have three different states that it can exist in. If you have you have an input A that goes into the buffer, you also have an enable. If the enable is 0, we'll show here, when we have the enable 0, we get a undriven value at the output. So it's not unknown. It will be unknown, but it's basically undriven. It has no active driver on the output. When the enable is a 1, we'll get an output that is strongly driven, either 0 or 1. So you can get three different states. You can either get a 0 output, you can get an output 1 output, or you can get an undriven output. Now normally being undriven output is a dangerous thing because you don't want unknown values or undriven nodes in your logic. So what do we do with this type of gate? So we can notice if we go and compare tri-state to pass gate, the transmission gate that we were talking about earlier can act as a tri-state buffer. It only has 2 transistors, so it can be pretty small. And if you put an enable in, where the enable is 1, enable bar, of course, is going to be 0, you will get a value through y that will be equal to A. And so you get, this acts exactly like we just talked about tri-state buffer. So you get an output y equal to A when the enable is on. When the enable is 0, you get no driven value through it, and so you get a Z state out. The thing to note about a pass gate tri-state is the fact that the value A is in effect directly connected through the switch of the N and PMOS device to the output Y. So if there's any noise on A, you will get that noise just pass through to the value Y. So it's called a non-restoring type of buffer, where it doesn't cause, if A is not fully up to a 1, the output Y is not going to be fully up to a 1. Normally our other complementary gates that are inverting will actually restore, even if there's a little bit of noise on some of the inputs, it will actually restore that back to a full VCC or ground value. So pass gate is a tri-state buffer, one type of tri-state buffer, but it's non-restoring. So a different type of tri-state buffer is a tri-state inverter. This differs from a pass gate as a tri-state element in that it actually inverts the input to the output, and it also requires more gates or more transistors. So you can see on the left side we see the transistor diagram for a tri-state inverter, where what you do, it kind of looks like a normal inverter from the standpoint of A, where you have A connected, the input A connected to an N and a PMOS device, but the enable device, there's an N enable and a P enable bar gate device that are connected in series with the transistor connected, or the N and PMOS transistors that are connected to A. What this allows us to do is when enable is low, then enable bar is high. That's the middle case up there. Both of the enable devices, P and NMOS devices, are both switches that are turned off. And so we have no path to either VCC or VSS. So we have the output Y is undriven, and so it's in that Z state of undriven. When the enable is high and enable bar is low, both the enable N and PMOS devices are switches that are turned on, so they're short circuit, and now our gate or the rest of our logic connected to A looks like a normal inverter. And so you just get the output Y is the inverted value of A. So the thing to note about this is because the N and P stacks are no longer complementary, this is something that basically violates our conduction complement rule that we had discussed earlier. But we're doing that for a specific reason, because we actually want to use this in a greater circuit where we want the Z as an output for this particular gate. So now that we've talked a little bit about tri-state logic, let's look at some logic areas where tri-states might come in handy. So one such case is multiplexers. So here's an example of a 2-to-1 multiplexer. What that means is we have two inputs, D0 and D1, and we want a select to choose between whether D0 goes through or the value of D1 goes through to the output. So in this particular case, if your select is a 1, we want the value of D1 to go through to the output, and the chart off to the left is showing that we don't care what the value of D0 is. The X's there mean it doesn't matter whether it's a 0 or 1, because we're only selecting D1. And if the select is 0, we want the value of D0 to go through. We don't care what the value of D1 is, so we have X's in there. So the output Y, if your select is 0, the output Y will be a 0 if D0 is 0, and it'll be a 1 if D0 is 1. If your select is a 1, then your output will be a 0 if D1 is 0, and it'll be a 1 if D1 is 1. So this shows how a multiplexer functionally, how we want it to behave. So now that we know functionally how a 2-to-1 mux behaves, let's look at the logical description for how a 2-to-1 mux could be written logically. So the equation at the top here shows the logical description of a 2-to-1 mux. So the logical description is the select value S and D1, or the inverse of S and D0. Because when select is chosen, we want to choose D1 value. So S and D1 will give us the value of D1. Or if select isn't chosen and S bar is high and true, then we want to choose the D0 value. So when S is low, S bar is high, and we take S bar and D0. And then we take the OR, whichever one of those is true, and that's the value of the output. So the question is, if we wanted to implement that logical function in terms of our complementary logic, how many transistor would we need in order to do that if we had the value of S, the value of D1 and D0, and we're just using the complementary gates that we've been looking at so far. So I'll give you a minute, and if you want to pause here, I'll give you a minute and try to map out how many transistors you think would be needed. Okay, so let's look at the logic that we would need based on what's written there. So we have here shown that we need S and D1, so we have an AND gate between D1 and S. Then we need S bar, or S inverted, and D0. Well, we don't have, so we need to take S and invert it, so we have an inverter there. Then we send the value of D0 and the inverted value of S into a second AND gate, and then we take the output of those two AND gates and go into an OR gate. The thing is, though, we don't have AND gates and OR gates. The way that our complementary CMOS logic works is we either have NAND gates or NOR gates, and in order to produce an AND, we need to take a NAND and then follow it by an inverter. So the overall function that we wind up getting when we use our complementary gates, CMOS logic, is we have inverter followed by basically the two NAND gates followed by inverters, and then a NOR gate followed by an inverter. Each of the NAND and NOR gates have 4 transistors each. Each of the inverters have 2 transistors each. So if you add all that up, you get 12 from the AND and OR gates and an additional 8 for the inverters, which gives you basically 20 transistors would be needed if you implemented this logic as shown. Now, instead of using the complementary logic that we had on the previous slide, what if we use the transmission gate muxes, or transmission gates that we've previously looked at, in order to try and create a 2-to-1 mux out of it? In this case, you can see that we still need S and S bar. So in reality, if we only had S available, we would have to have an additional inverter in order to create S bar. So there should be really 2 more transistors shown if we wanted to implement this with only D1, D0, and S. But you can see for each of the transmission gates, we only have 1 PMOS and 1 NMOS transistor. And so total number of transistors is we would have 4 transistors for the base mux, plus another 2 transistors would be needed in order to produce S bar. So the total number of transistors to do the same function as we saw previously, we would need 20 transistors using all of our CMOS gates. Using this transmission gate mux, we would only need 6 transistors if we needed to produce S bar. So the only downside, or one of the downsides, of this 2-to-1 mux using transmission gates is it's non-restoring. So again, if you have noise on the D1 or D0 values, you will have noise on the output as well. So you might or might not want to use this depending on your usage. If you know that you have strongly driven D1 and D0 signals, this is fine to use. If you're not sure, you might want to use a different type of logic. So instead of making a non-inverting mux, what if we wanted to make an inverting mux? So if we took that same logical function that we had a couple slides ago, where we had y was S and D1 or S naught and D0, and we made it a NOR instead of an OR. That would allow us to, as I have said previously, if we have an inverting function, we can make any inverting function using complementary N stack and P stack. And so we can create what's called a compound and OR function. AOI 22 is the designation that they call this particular thing. And if you look at that logic in the lower left, we have the N stacks would be S and D1. So you have 2 series stacks of, or 2 NMOS transistors in series, S and D1 is the right-hand NMOS stack. And then we have S0 and D0, so there's two more N in series with each other going down to ground. And then since this is a NOR function of those two ANDs, we put those two N stacks in parallel with each other. And then again on the top, we would take two P stacks or two P combinations where the D1 and S are in parallel, and then the D0 and S bar are in parallel, and then those two combinations of P parallel devices are placed in series with each other, and that would give us a complementary N and P stack. Now, the thing that you can note here is if we kind of break the connection between the two P stacks, in effect, it winds up looking like our inverting tri-state inverters. So if we take a tri-state inverter with D1 and another tri-state inverter with D0 and place them both in parallel, basically driving the same output node, we get the same logical function. And so of course the D1 and D0 selects are flipped between D1 and D0. And that allows us to, even though one stack or the other stack is always turned off, when the D0 device is tri-stated, the D1 device is turned on solidly, and vice versa. When D1 is tri-stated and not on, the D0 stack is going to be driving. So this allows us to get that mux function, but it's an inverted mux. And if we wanted to create a non-inverted mux out of this tri-state type mux, we can just add an inverter at the output. Now you can see here the total number of transistors you need in this particular case is 8 transistors, 4 for each tri-state device. And then if we wanted a non-inverted version coming out, we'd need 2 more transistors, which would bring it to 10. And if we didn't already have a select bar coming in and we needed to invert S in order to create S bar, we would need another inverter for 2 more. So the total number of inverters or total number of transistors for this stage could be as high as 12 if we didn't have an S bar available and we wanted a non-inverted signal coming out for Y. But that's still less than the 20 that we had calculated for the other version of a non-inverting mux. So now that we've seen how to make the simplest, a couple different options for making a simple 2-to-1 multiplexer, let's look at a more complex 4-to-1 multiplexer. This is where we'll be choosing 4 different inputs, and we want to choose which of those 4 different inputs, D0, D1, D2, or D3, gets basically translated to the output Y. And we, in this particular case, have 2 separate selects, S0 and S1, that we can use to determine which of those 4 inputs goes to the output. So on the left-hand side, we can see one option is we can use 2 separate 2-to-1 muxes, one of them choosing between D0 and D1, another one choosing between D2 and D3. That produces 2 outputs that can go into a following 2-to-1 mux to choose whether you take either the D0 D1 path or the D0 D2 D3 path and send it to the output. That combination will allow you to choose any one of the 4 inputs to go to the output. Since each of those 2-to-1 muxes is being shown as one of the inverting 2-to-1 muxes, the output will be a non-inverted version, since it will get inverted in each of the series 2-to-1 muxes. So 2 inversions equals a non-inverted output. So let's compare that to the right hand side, where what we've taken is 4 tri-state device gates, and one each for D0, D1, D2, and D3, connected them in parallel to drive the output Y. Now we need 4 separate selects, one going to each of the D0, D1, D2, and D3, and again 4 inverters in order to create the inverted version of the select in each case. Now the selects in this case, you can't just use the raw version of S1 or S0, you actually have to kind of decode them, because you only want to choose D0 if both S0 and S1 are both 0. So the notation that's used up at the top there of the right hand figure is S1 ANDed, or S1 inverted, so S1 bar ANDed with S0 bar, it would be used to choose D0 to be the tri-state that's on. Likewise, for D1, you want S1 bar ANDed with S0, and likewise for the next two, they each need to be decoded in order to get the select that's being used for them. So in both of these cases, if we try to compare the number of transistors that would be needed, so the left hand side, each of those 2-to-1 muxes would require, as we said before, 8 transistors inside the 2-to-1 mux, but since we don't have an S0 bar, that implies that inside of that 2-to-1 mux is an inverter that produces S0 bar that's needed inside the 2-to-1 mux. So there will be 10 transistors used inside each of these 2-to-1 muxes, including the inverter needed to invert the selects. So since we have 3 of those 2-to-1 muxes, that means we have 30 transistors being used in the left hand figure. In the right hand figure, each of the tri-state devices only has 4 transistors, and each of the inverters has 2, so each combination of tri-state and inverter is 6, and we have 4 of those, so 6 times 4 is 24, which is less than the left hand side, but we haven't included the decoding that needs to be done in order to produce the selects. I mentioned each of those selects would require an ANDing of either S1 or S0, or some combination of S1 and S0 and S1 bar, S0 bar. So that decoding, since that's not shown there, would wind up adding quite a few more transistors if we didn't have both S1 and S0 and their bar versions available already, or some decoded versions of those selects. So it's quite likely that the right hand side one would wind up actually requiring more transistors than the left hand side one in this particular case. And also keep in mind, the right hand side figure is actually going to give you an inverted version of Y out, because it's only got a single inversion through those tri-state devices. So you get a slightly different function than the left hand one, and you have to decide whether you have already decoded the selects or not someplace else on which one is more efficient to use.